schematic. In former class, we had learned the processor had level 1 storage, and the other components have other levels. You can find level 1 and smaller, faster, and more expensive storage. Level 1 has bigger, slower, and cheaper storage. So we have learned the hierarchy is shown by this image. So please remember this image, and you will find this image in several conditions. In computer organization, we had discussed the hierarchy, the storage hierarchy, or memory hierarchy. Okay, let's continue. You can find the cache. It is important memory, and cache holds a copy of a subset of main memory. This is different. This is important. You can find one variable in cache and main memory. If the two values are different, which is trusted? We have trusted cache. If one variable has two values, we have trust cache. So our method is simple. Use the cache value to replace the main memory. So we trust cache. So you can find we also use one symbol to abbreviate cache. So you can find modern processors have separate caches for instructions and data. You can find modern processors have several caches, level 1, level 2, level 3.
Yeah.
Level 1, his size is smaller. Level 3, his size is bigger.
More bigger than
level 1.
Level 1.
Yeah. So you can find level 1, level 2, level 3. But the speed is slower. The speed of level 1 is faster. The speed of level 3 is slower, but it is big than main memory. So you can find it is a hierarchy and period. So you can find the shape of hierarchy is like period.
Yeah.
金字塔. Implemented with same IC processing technology as CPU and integrated on chip. Integrated on chip is future technology. Integrated on chip. Yeah, you can find with our cell phone is powerful. The reason is the powerful CPU in cell phone, not in computer. So you can find integrated on chip is faster but more expensive than main memory. So you can find our current modern cell phone, the price is high and high.
Yeah.
The price of higher of modern cell phone is like a laptop, 5,000, 6,000, even though 10,000. Okay, you can find the memory transfer in the hierarchy. You can find this is the flow. In processor, we transfer from 4 to 8 bytes. In level 1 to level 2, we can find we transfer by block. Block is the size. You can find 8 to 32 bytes is the size of block. Sum of block is 8 bytes. Sum of block is 32 bytes. So you can find in this level 2 to main memory, you can find one block is from 16 to 128 bytes. So you can find the block, size of block become big and big. It is correct because in the main memory we transfer the data, the size of data become big and big is useful. And you can find from main memory to secondary memory, we can find this size is become bigger. So block is unit of transfer between memory and cache. So you can find this is block. This is page. Page is one big size. So you can find one book. You can find we can see this is page. And in the book, this is the line. This is page. So this is the unit. Okay, we can find managing the hierarchy. The three questions or the three sections. One is register and memory. Yeah, register and memory. His operation is current frequently. From register to memory, the operation is frequently. Yeah, 频繁，经常发生。Yeah, frequently. By compile and or assembler, we can find we use some compile software to design our program. Our program code can transfer register to memory. Cache to main memory, we are discussed in the section. We can find by the cache controller hardware, we can use cache and main memory. But please remember, the size of cache is 10. The main memory, the size of main memory is 10 than cache. So the size of cache is main memory.
Okay.
Yeah. If the main memory has 4 GB number, then cache, the size of cache. But please remember, this is the whole cache. The cache has 3 levels. This is the whole size.
Yeah.
So you can find main memory to disk in secondary storage. So you can find the secondary storage is a formal term to represent the disks. By the OS operating system, virtual memory, you can find the virtual memory in disks. Virtual to physical address mapping assisted by the hardware. You can find some hardware is called TLB. This is TLB is a size unit from the hardware by the program files. Okay, this is the size of main memory or memory. This is the small unit. This is the large unit. You can find K, M, G, T. The size of disk is current T. So you can find you can buy one disk. Its size is 1T or 2T. So the disk size, the size of disk is bigger and bigger, but the secondary memory size is bigger. The speed is lower. The speed is slow. So we can use the secondary memory to store our data, but he is the author of the scape. This side we talk about cache. This side we talk about level 2 or level 3. This side we talk about DRAM or main memory. So 4 GB or 8 GB is current main memory. Yeah. So you can find in the market the current computers, the main memory size is 8 GB or 16 GB.
Yeah.
Our students want to have more and more main memory, so they like by 16 GB main memory. He is very likely the students like the main memory because he is run some big software like play game.
Okay.
Yeah. So some students like play game, but our teachers isn't like games. Teachers like main memory because our experts run need more main memory. Okay, this is Jim Gary. Jim Gary is a famous Turing Award scientist. You can find Jim Gary, this name from website. So you can find the storage, latency, analog. His question is how far away is the data. So you can find register is 1 minute and the disk is 2 years. He gives the times. Okay, we can find the two sides, two different main memory. Let's see.
Okay.
This is
I want to see the big
what? This is disk, memory, cache, and the register. This is his running time. He gives the weight of the data. So he gives an example. Jim Gary is from he is give this question in many years. So this is not correct. So don't worry. Okay, please see SRAM and DRAM. This is important. SRAM is static RAM. What is RAM? Read abandoned memory. So you will remember RAM is read and write. ROM is only read. So you can find RAM. SRAM is used for cache. So you can find SRAM is typical access times from 0.5 to 2.5 nanosecond. He is powerful. He is higher powerful and expensive. So you can find in 2011, this is the price per GB. He is very high. 1 G is cost $2,000. So we can't use it. He is powerful. He is expensive. It is expensive. Okay, static is content will last as long as power is on. So SRAM is very useful, but the size of SRAM is small. So we use SRAM to cache. Okay, DRAM. DRAM is dynamic RAM. Dynamic and static is different. Yeah, dynamic RAM is become big and big, his price is lower and lower. So DRAM can become main memory. But DRAM has shortcomings. What shortcomings? The DRAM, if we have electricity, the DRAM becomes zero. So the DRAM is running by electricity. So we must give the power to the computer. The DRAM can store the data. If we haven't electricity, the DRAM becomes 0 and 0.
Volatile.
Yeah. So you can find typical access times of 50 to 70 nanoseconds. Dynamic needs to be refreshed regularly. So you must remember this word, refresh. What is refresh? In Chinese we call 刷新. Yeah. It's like wash. Yeah. If we don't wash this classroom, the classroom will become dirty and dirty. If you want to, the classroom become clean, so you must wash. So you can find refresh is like this operation, refresh. So every 8 milliseconds, we must refresh the DRAM. Okay, you can find the goal and the approach. Present, the programmer will equal as much memory as the largest memory, equal the speed of the fastest memory. Approach is memory hierarchy. So successively higher levels contain most used data. From lower levels, we will start by studying caches. So you can find cache is important memories. Okay, we can give some problems. What is the overall organization of blocks we impose on our cache? Where do we put a block of data from memory? How do we know if a block is already in cache? How do we quickly find a block when we need it? When do we replace something in the cache? This is the problems the authors giving us. We can find this is the operation. Okay, you can find memory is byte address. We call this is recall. We haven't specified the size of our blocks, but will usually be multiple of word size. So how do we access individual words or bytes within a block? We can find offset is the solution. Cache is smaller than memory, so you can find we can use one method. It is index. If you have learned database, index is the technology of database. Do you learn the database database course? In database course, index is very useful label in the database. So if we have index, we had find some wanted data by index. So the database technology is very useful and very important in bank, in communication, in some related companies. So in Huawei, in Tencent, in Alibaba, index is very useful. We can see in Taobao. In this website, you will find it is giving us the index to find the what is something. Yeah. He gives us index. Okay, tag is like index. What is tag? Tag is a label. Needs some way of identifying which memory block is currently in each cache slot. Slot is a unit from cache. Okay, we can see a whole subset of memory in a place that's faster to access. We can run data to you when you request it. If cache doesn't have it, then fetch it for you. Cache must be able to track or identify its current contents. What does cache initially hold? We can find the garbage. You can find the cold and the hot. In cache, we like hot data. We don't like cold data. What is cold data? Cold data is recently unused data. If some data in cache don't used recently, the data hasn't used. So we think this is cold data. Hot data is used and used frequently. So we like hot data. We think we want hot data in cache is good thing. Cold data is bad thing. So we must replace the cold data out of the cache and replace the potential hot data in cache. We don't track the data is hot, but we can suggest, we can recommend, we can guess. So keep track with valid bit is the cache. Effect of block size is key bytes. Spatial locality. Spatial locality dictates our blocks consist of adjacent bytes which differ in address by 1. Offset field is the size. Lowest bits of memory address can be used to index to specific bytes within a block. So the offset is the distance or the some sub-distance. So we can use the red offset to represent the 8 block. The red X is the thing for all bytes in block. This is the size. Okay. This is some question. You are given a 2056 byte cache that holds 8 date blocks. We are working on one 10-bit byte addressed machine, which statement is false. We can find this is the solution. Section A. Each data block holds 32 bytes of data. You can find the blocks equal cache size or block size. So 32 bytes is correct. The section B, our tag can be more than 5 bits. We can find offset bits equal log operation equal 5. Tag bits equal 10 sub 5 equal 5. So all the main memory could fit into 4 caches. This is 10-bit addresses equal 2 equal 10 bytes of memory. 2056 bytes equal 2 equal 8. Multiple 2 equal 2. This is 2 equal 10. This is the result. So this is 1024. The section D, only one valid copy of a block can be in the cache at any point in time. This is the current. Okay, fully associative cache, we can find each memory block can map anywhere in the cache. This is fully associative. Most efficiently used of space, least efficiently of to track. To track a fully associative cache, we can look at all cache slots in sequence. If valid bit is 0, then ignore. If valid bit is 1 and the tag matches, then return that data. This is the correct result, and the cache must store valid and tag bits. Fully associative cache address breakdown we can find in memory. We use two addresses. One is tag, one is offset. So tag has tag bits, offset has offset bits. Yeah, this is offset bits become 2 equal offset bytes per block. Tag bits equal A sub offset, where A is the address bits. So A is 32 here. Oh, this is another question. You can give one 32-bit byte address machine, then offset field is 5 bits, but you decide to use only 26 bytes to represent the tag. Which of the following states is true? We can find the section D. You cannot properly identify what is data block is in the cache. The discrimination is if I ignore the last tag bit, how can I tell this symbol and this symbol? So you can find this is the correct. Okay, fix, miss, and replace. We talk about policies. What is policy? Policy is the method.
Yeah.
When reading memory, two things have happened or can happen. One is hit, one is miss. What is hit? Hit is I got it, our wanted data. Yeah. We find our wanted data in cache. This is hit. We don't find our wanted data. This is miss. So hit is current operation. Miss is
there's something wrong.
Yeah, there's something wrong. Yeah, cache does not have desired block, so fetch from memory and put it empty slot. So you can find this. If the cache had miss operation, with the solution is fetch from main memory. So if cache haven't our wanted data, we have used the main memory to second memory. If cache is full, you must discard one valid block and replace it with desired data. We can see the memory. We can find the data from memory. Block replacement policies. Replacement is frequently operation in cache. We must hold the hot data in cache. So replacement is frequently operation. Which block do you replace? How did the cache to discuss or to justice the data is in cache or it isn't in cache. So use a cache block replacement policy is the solution. There are many, but we will just cover a few in this class. This is the website. Random replacement is a normal method. Random replacement is random. 随意替换. If we have some, if the cache is full, we want the cache free some size. Random is the normal method. What is random? Random is random.
随便.
Yeah, 随便. List recently used is a current solution. Is a correct solution. Here is LRU. LRU is list recently used. Requires some management bits. So LRU in Chinese we call 最近使用. 最近最少使用. So list recently used. So if the data is list recently used, the data is cold. The data is being refreshed. Okay, we can understanding LRU. The best replacement policy we could have is to replace data. We will use fastest in the future. Either never use again or use later than everything else. Unfortunately, this isn't possible. Instead, we approximate using LRU. Replace block, we use the list recently first in the hopes we will use it again later than all other blocks. Okay, we find how effective is your cache. We want to max cache hits and min cache misses. So we hope the cache hits can reach 100 per This is our hope. The fact is 97. Yeah. If the cache hits can reach 97, this cache is useful. If the cache hits only can reach 60, 80, and less than 80, the use of cache is less. So we want more. We want max cache hits and min cache miss. So you can find HR and MR. HR is hit rate. MR is miss rate. HR add MR equal 1. How fast is your cache? You can find two terms. One is peak time, two is miss penalty. Peak time is time to access cache. We want this peak time become small and small. If the peak time becomes small and small, the use of cache is become powerful and powerful. If we had a smaller peak time, the speed of cache must become faster and faster. Peak time is current time. Miss penalty is showed some error. Time to replace a block in the cache from a lower level in the main hierarchy. If we had hadn't data in cache, we must find the data in main memory. So the main memory, the speed of main memory is slower than cache. So the total cache, the total speed is higher and higher. What's actually in the cache? Each cache slot contains the actual data block, one block per slot in FA. FA is physical address. Not physical address. This is address. This is frequently address. Yeah. Tag the field of address as identifier, valid bit, any necessary replacement management bits. You can find this is the equation. Okay, what does a cache look like? You can find the fully associative cache is like the data path, and you can find if we have the cache, we have the data. Okay, as a cache example, we can find SA, fully associative address space of 64 bytes, block size of 1 word, cache size of 4 words, address breakdown, and the memory addresses. You can find this is block addresses, bytes, bits in cache. You can find this is the calculation. Okay, this is cache parameters, fully associative address space of 64 bytes, block size of 1 word. We can look. This is one SA cache example. This is complex example. We find the step 1 is configure the sequence of memory address successes. We can find some values in arrays must be hit, and some values in array must be missed. Okay, we don't care. If you have time, you can look some example from cache in website. But the example of cache is very complex. So if you have some mice and some you want to see, you can see. If you don't want to see the example of cache, you can't care. Okay, memory accesses, we can try to image CPU, cache, memory, main memory. This is myth and data. If we have a hit, we use the cache to return the data to the CPU. If we have the miss operation, we have the data from the main memory. From the main memory to cache and to CPU. So if we had miss operation, the time of operation is become long. Cache is separate from memory. We can find this is another question. Okay, we can find the read and the write is the two important operations in memories. We want to handle reads and writes quickly while maintaining constancy between cache and memory. Quality of cache hits and misses are independent. Here we assume the use of separate instruction and data cache we can use read and write. This is two important operations. This is handling catch hits. We can find the read hits and the write hits. Read hits is fastest possible scanning, so want more of them. Write through policy is one policy. It is always write data to catch and to memory through catch. So write through in Chinese we call 写贯穿. 写贯穿. Write through. Yeah. In Chinese is 贯穿. Forces catch and memory to always be constant. This method is slow. Every memory access is long, so this method is not good. You can find the speed is slow. This is important error. We can find include a write buffer. So you can find the buffer. Buffer is same to catch that updates memory in parallel with processor. The assume is assumed present in all schemes when writing to memory. Okay, the two solution is write back policy. Write back is write data only to catch, then update memory when block is removed. If the data in the cache, the data is in the cache. If the data out of cache, we had stored the data to the memory. So we can find allows cache and memory to be inconstant. Multiple writes connected in cache, single write to memory per block. So dirty bit is existing. What is dirty? Dirty is 重复 duplicate. So dirty bit is duplicate bit. So if we have duplicate bits, we find each bit per cache row that is set each block was written to. This is dirty and needs to be written back. So dirty is the circumstances. Okay, let's have a rest.
আজকে ব্রেক কেন দিল আগা আছে
এবার এই সেমিস্টারে মানে কি বিনোদন গুলা সবগুলা খোলাবেন করতেছে
ওরা ফাইনাল যখন বিনোদন হইলেও না হয় কি বলেন আমার কথা কি যুক্তি আছে এই রিভিউগুলো দিয়েছেন এই রিভিউগুলো এখানকার এই রিভিউগুলো ঠিক আছে এই নম্বর না ঠিক আছে ঠিক আছে ঠিক আছে আমি ইউজ করতেছি পাবে তো ঠিকই আছে আমাদের ধর্ম এখানে কেউ আমাদের ভিতর থেকে আমার সবসময় দিতে চায় এটাই কোনো ক্যারেক্টার এটাই বাবা সেখানে শ্রদ্ধাও করি আমাদের লোকাল টেলিভিশনে আমাদের লোকাল টেলিভিশনে
টেলিভিশন মানে চ্যানেল এমনি ওই আমার
ডিজাইন লাগবে
সি প্লাস টিভি আছে একটা ওই সংবাদের চ্যানেলটা তো মাঝে মধ্যে ইয়ে করে আর কি সি প্লাস টিভি
শব্দের কারণে সাবধানী হতে হবে
이번에 보내 갔어요. 오늘 수스로서 도쿄에 하는 정도. 이 시점 아마 이걸 남는 기억을 뭐라고 다른 분들이 있어요. 우리 가지고 아주 멀어서 다시 멀어지는 분들이 맞다같이 알고 야 오늘 비싸 많아요. 이거는 왜 안 그래?
Okay, let's continue. Please pay attention to the weather. The weather is cold. Yeah, several handle catch misses. We can find the miss is not good operation. He has some errors. Miss penalty grows as block size does. So we find if the block size is become big and big, the miss penalty is become big and big. So the block size we check the block size isn't big. He has some latency or has some limitation. So you can find the miss penalty grows as block size does. If we have read misses, we can find the store execution fetch block from memory, put in cache, send requested data to processor. Resume. This is read misses. Write misses always have to update block from memory. We have to make a choice. Carry the updated block into cache or not. This is one question to check. Write allocate policy. Write allocate. When we bring the block into the cache after a write miss, we have a write allocate policy. We have no write allocate policy. No write allocate policy only train main memory after a write miss. So we like no write allocate policy because this method is depend on the time. So we can find write allocate almost always paired with write back. So write back is better than write through. Write back 写回 write through 贯穿. So we like write back. No write allocate typically paired with write through. Okay. Updated cache picture, we can find this is same as previously shown. We can write miss procedure and we can find only effects behavior, not design. Okay, this is the summary from memory hierarchy. We can find the memory hierarchy exploits principle of locality to deliver loss of memory at fast speeds. Fully associative cache. Every block in memory maps to any cache slot, offset to determine which byte within block. Tag to identify if it's the block you want. Replacement policy has random and ALU. Cache parameters has block size and cache size. So you can find block size and cache size has limitation. Cache write places, write back, and write through. We like write back. Write back is better than write through. Okay, this is the full content in lecture 15. Please see lecture 16. You can find the lecture 16. Direct match and set associative cache is the main discussed topic. This is the last lecture. This is the last section. Yeah. Okay, we can find fully associative caches. Every block can go in any slot. Memory address breakdown. Each cache slot holds blank data tag, valid date, valid bit, and dirty bit. This is the extended review. On memory access, we can read and write. Look at all cache slots in parallel. If valid bit is 0, then ignore. If valid bit is 1 and the tag match, then use that data. So, on write, please see set 30 bit is write back. Okay, we can see handling write hits. Write hits have two policies. One is write through policy. One is write back policy. Please see. Write through policy always write data to cache and to memory through cache. Write data only to cache, then update memory when block is removed. So, dirty bit is extra bit per cache row that is set if block was written to and needs to be written back. Handling cache misses, miss penalty grows as block size does. You can find the read misses and the write misses. Write allocate policy. No write allocate policy is the topic in former class. Okay, we can see updated cache picture. We can through write and through write back to operate. Okay, how do we use this thing? We can see nothing changed from the programmer's perspective. Still just issuing. LW and SW is the load and store instructions. The rest is handled in hardware. He can checking the cache. Tracking the data using the offset. So offset is important distance. Why should a program care? We find understanding cache parameters equal faster progress. Okay, we can see direct map cache and set associative cache and discuss cache performance. So we can look direct map cache. This is a simple policy. What is direct map? Direct map is, in Chinese we call 直接映射. Direct map. Each memory block is mapped to extract one slot in the cache. This is direct map. So if we have one data needed by CPU, the data must in the cache. If the data isn't in the cache, we must put the data into the cache to prepare to the next operation. If the next operation, the CPU wants the data again, the cache must hold the data. So we find the data. If the CPU wanted, the data must in cache. If the CPU don't want the data recently, the data must be replacement. Comparison with fully associative, we can check just one slot for a block, we can find no replacement policy necessary. Access pattern may leave empty slots in cache. Okay, direct map cache has three fields. One is index field, two is offset field, three is tag field. Index field specifies the cache index, which slot of the cache when we should look at. Once we found correct block, specifies which byte within the block we want. The remaining bits after offset and index are determined. These are used to distinguish between all the memory addresses that map to the same location. This is three fields. Okay, this is an example in direct map cache. So you can find from the left is memory, main memory. The right is cache. So you can find this is important. Cache location 0. Cache location 0 is here. Can be occupied by data from memory location 4 blocks. So you can find they tell us 4 byte direct is this has 4 bytes. Per line has 1 byte, has 8 bits. 1, 2, 3, 4. This is 4 bytes. So we have 4 lines in cache. In main memory, we have 16 lines. So this is the cache is small, the memory is big. But this is an example. The fact is not so simple. So you can find we use 0, we use 4, and we use 8, and we use 6. You can find 0, 4, 8, 6. So you can find the location 0, 8, 4, 4, 8, 6. This is the selection in cache. If you choose one line in main memory, we choose the main memory to the cache. This is direct map. It is simple and it is well operated. Because it is simple, so it is well operated. Okay, this is TIO address breakdown. We can find it has tag, index, offset, 3 fields. And the meaning of the field size, you can find O bits, I bits, T bits. This is T bits, I bits, and O bits. This is not 0. This is O bits. This is the size. Direct map cache. We can find what's actually in the cache. We can design the block of data. Tag field of address as identifier. Valid bit, direct bit, no replacement management bits. This is the inclusion and the calculation. Okay. The memory hierarchy is very important. So I hope you can look some extra materials in website and from Baidu, from some searching engine to extend your minds to hierarchy, memory hierarchy. So memory hierarchy is current solution for computer, for the speed of computer. If we have better memory, the memory hierarchy must be destroyed. But this is the future. We can see in current computer the memory hierarchy is very important and very useful. So please search some materials to see some hierarchy, memory hierarchy. So because I will tell me in next Tuesday you have appointment.
Yeah.
To some operating. Please keep safe and be safe. Okay. Now see you in next Thursday.
Thank you.
Okay. Okay. Thank you.